My name is Yue Chudo, and I'm from SecureWorks, and I provide red teaming services for enterprises mainly in Japan. So for today's talk, I'd like to share one of the challenges that I had during our red team engagements, and also I'd like to share the solution to it. Now, here are the agenda for today's talk. First, introduction, and then we will move on to the device authentication mechanism of the Microsoft Entra ID. And then, after that, we will dive into the device authentication internals, the Windows internals, and also I'd like to talk about how to abuse it with demo, and mitigation, finally, conclusion. So, introduction. So let me begin with a story from our red team engagement. So one day in our red team engagement, we successfully spearfished and got one of the target machine infected with a Shizu client. So from the machine, we broke into its internal network, and with some techniques, we compromised the target Active Directory with some techniques, and we got the domain admin privilege. So after that, with the DA privilege that we got, we dumped all the credentials from the Active Directory. And in the dumped credentials, one of the credentials looked like admin account in Azure AD, currently which is known as the Microsoft Entra ID. So if we can successfully log in with this admin account of the Azure AD, we might get admin access to Entra ID as well, right? So we try to crack its password, and we try to log into Entra ID with a credential. However, the login was successful, but the access was blocked by one of the security features of Microsoft Entra ID, which is the conditional access. So what is conditional access? For those of you who are not familiar with the conditional access, this is a security feature by Microsoft that can control access to resources in the cloud based on the signals like who you are and what your device is and what application you are using and what your network, etc. So from the error message that we got, we can tell that the access was blocked by the device-based conditional access policy, and it seems it requires the Microsoft Entra and on-premise AD joint device, which means that we need, as attacker, we need a corporate device for pivoting to the cloud. So the question is, how can we bypass this kind of conditional access policy where you need a specific device? So from this engagement, I started researching into how we can bypass the device-based conditional access and gain access to resources as any user with a credential. So we want to access to resources in the cloud as any user with a credential, not just only the logged-on user of the device, so that we can easily switch accounts, move laterally between accounts for further post-exploitation activities in the cloud. So this is my research goal. So to get some ideas for the research goal, let's look into the mechanism of how Entra ID can identify device during the authentication. So the important part of the device identification by the Entra ID is the keys generated during the device registration. So when device is registered to Entra ID, two key sets are generated. One is the device key, and the other one is transport key. And each of the key sets has its public key and also the private key. And during device registration, the public keys of the device key and also the transport key are sent to Entra ID and registered. And after that, Entra ID can identify device based on the usage of those keys during authentication. So now let's look into the detail of the authentication flow when you access to Microsoft with your browser and from your corporate device. So first, when you want to authenticate to Entra ID with your corporate device, and device sends the login request signed by device key. And the signed login request is basically JWT, which is the JSON Web Token. And the JWT has three parts, and each part is base64 URL encoded JSON values. And the first one, header, defines the signing algorithm of the JWT, And the second one, payload, contains username and a password for the user authentication. And the last one is the signature, which is the JSON web signature made by device key. So Entra ID receives this request and verifies the valid key usage of the device key and also the credentials in the payload. So by sending the signed login request, Entra ID can identify device and authenticate user. Then Entra ID returns PLT, which is the primary refresh token, and also the session key. And this is the response from the Entra ID. And in the response, you can see there is the PLT and also the session key right there. And one primary refresh token is this can be used for single sign access to the, for example, Teams or SharePoint or Outlook or whatever. You can use it for single sign-on. But just sending PLT is not enough for the single sign-on. You need to use the session key as well. But in the response, session key is encrypted, actually. And to use the session key, device decrypts the encrypted session key by transport key. So for the single sign access with your browser, first device decrypts the encrypted session key in the response, and then use it to sign the PLT. And this one is called the PLT cookie. And PLT cookie is also the JWT, as you can see there. And it contains the PLT in the payload like this. And this PLT cookie, its JWT is signed by the session key, which is bounded to a specific device. So again, Entra ID can identify which device is used from the key usage of the session key. And also, Entra ID can control the access to resources in the cloud based on the device information. So after the device identification, you can access to Microsoft. You can access to the resources in the cloud like this. So in summary, during the device registration, device key and transport key are generated and registered to Entra ID. And then Entra ID can identify which device is used by the signature of device key and also the session key. But the session key in the response is encrypted, so device decrypted by the registered transport key and use it to sign the PLT and create a PLT cookie. So getting back to the research goal, from this mechanism, we can say that by signing any user's login request and also the PLT with those keys, then we can access to Entra ID as a registered device and bypass the device-based condition access. However, those keys, the device key, transport key, and also the session key, all of them are securely stored in TPM, the Trusted Platform Module, if the device has it. And those keys cannot be exported. They are not exportable. And there is a prior research, and the exporting a derived key of session key and creating PLT cookie is discovered by Benjamin Delphi and Decryption. However, it is patched in 2021, so currently it is hard to export those keys and create PLT cookie. But even if the keys are protected in TPM and not exportable, I believe that still those keys can be used from the device. And they can be accessed, I believe. So if we can understand how the TPM stored keys are handled and used in the device internally, then we can still abuse them for creating any user's PLT cookie and fake device to access to Entra ID. So this is why I started reverse engineering Windows OS to understand how those secret keys in TPM are used and how we can abuse that. So let me talk about the analysis of the Windows internals and the ways of its abuse. First, I started researching how Google Chrome handles the browser single sign-on, especially its extension called the Windows Accounts that handles the browser single sign-on for user. And so when you open the Google Chrome and access to Microsoft with it, what happens there is that first Google Chrome spawns a new process called browsercore.exe, and then browsercore.exe load a DLL called Microsoft Account Token Provider.dll. And then browsercore.exe executes a method inside a DLL called getCookieInfo for URI. And this method get the PLT cookie of the logged on user of the device and return it to a caller process and return it to a Google Chrome. So basically, this is a way of browser single sign-on for Google Chrome. And also, this has been abused by attackers for PLT cookie theft. What I mean by that is that attackers can use the browser core.exe, or attacker can also use the DLL and execute the method inside it. So, but for my research, I tried to discover what the method, the get cookie info for URI, does to internally get the PLT cookie of the logged on user for my research. So, if you look at the get cookie info for URI method in the DLL, you can find that the method at the end calls the LSA called authentication package. And this Windows API can communicate with the authentication provider loaded in LSAS. So this means that the method get cookie info for URI is sending some data to LSAS to get the PLT cookie of the logged on user. And if you look at the data sent to LSAS, then you can find some JSON data with call ID and also the payload values in it. And if you also follow where the JSON data goes, then you can tell that the JSON data is first sent to the cloud authentication provider in LSAS, and then the JSON data is passed on to the Azure AD plugin. And finally, the Azure AD plugin handles the JSON data inside this function. And inside this function of Azure AD plugin, there is a switch statement. And based on the call number of the JSON data, one of the functions inside the Azure AD plugin is executed. And this time, the call number in JSON is 2. So the create SSO cookie function inside the plugin is executed. And then this function returns the PLT cookie of the logged on user. So let me summarize what we have seen so far. So during the browser single sign-on, Google Chrome runs a browser core.exe, and then browser core.exe execute the get cookie info for URI. And then this method execute the LSA core authentication package to communicate with LSAS.exe. And by sending the JSON data passed on to the Azure AD plugin, then based on the call number of the JSON data, the create SSO cookie function is executed. And this function returns a PLT cookie to the Google Chrome. So this is what happens during browser single sign-on. And in order to interact with the LSAS.exe and also the Azure AD plugin for my research, I implemented a POC that can directly talk to LSAS.exe without the browser core.exe and also the DLL by just calling the LSA core authentication package. And with this POC, I was able to call the create SSO cookie in the plugin. So by replicating the same flow as Google Chrome and by executing the function inside the Azure AD plugin, I confirmed that we can steal the PLT cookie of the logged on user, as you can see there. So now I got another way of PLT cookie theft for the logged on user. However, the retrieved PLT cookie only allow us to gain access to resources as a logged on user of the device. And to access to resources as any user with the credential, first, what we have to do is that we need to sign the user's login request by device key. For this thing, there was an internal function in Azure AD plugin called sign-payload function. And it looked like interesting, and it looked like this might help with the research. So for my research, as a next step, I started looking at the sign-payload function inside the Azure AD plugin. So this is a part of the decompiled version of the sign-payload function in the Azure AD plugin. You can see there are two functions called inside this function. And one is the check package SID for request sign, and the other one is build device source assertion. So let's look at the second one first to understand what this sign-payload function inside the plugin can do for us. So what it does in the build device source assertion is that first JSON data is sent to LSAS.exe, and then the build device source assertion gets this payload value and base 64 URL encoded like this. And at the same time, JWT header is generated. And from the header and the payload, the signature of the device key is generated. And finally, combine all together, JWT is created with the signature of device key. So the sign-payload function literally can sign the content of the payload and make JWT with the signature of device key. So this means that with this function, if you include username and password in the payload of the JSON data, then through this internal function of Azure AD plugin, you can get this login request with the signature of device key. And you can use it to authenticate to Entra ID. However, there is another function, the check package SID for request sign. And what this function does is that this function checks if a Cora process SID is the one specified here. And if not the right SID, then the build device source assertion is not executed, and therefore sign payload function does not return the device key sign login request for us. However, by quickly searching the SID specified there, I found that the SID is for the app containers SID, and it is for the application called Azure AD Token Broker. Since this SID is for the app containers, with some techniques, we can impersonate this SID in the device, and we can bypass the SID check of this function. So for example, from our C2 client, we can impersonate the Azure AD Token Broker SID to bypass the SID check, and then we can call the LSA call authentication package and to execute, this time, the sign payload function inside the plugin. And if you include username and password in the JSON data sent to lsas.exe, then you can get the device key sign login request through this approach. So I implemented a POC for this approach and generated sign login request with the signature of device key, like this in the request. And by sending this sign login request, then I confirmed that we can get any users, the logon users, we can get the PLT of the user, and we can also get the encrypted session key in the response. So to sum up, we can sign any user's login request by device key through the internal function of Azure AD plugin called sign-payload. So by sending the sign request, we can get the user's PLT, and also we can get the encrypted session key. For the browser single sign access, we have one more thing to do, which is to decrypt the encrypted session key in the response and use it to sign the PLT with it. And so let's find out how we can do that. So by looking at the plugin code, I found that undocumented API from cryptongc.dll are imported and used for handling the encrypted session key in the response, which are ngc import symmetric pop key and also the ngc sign with symmetric pop key. I'm not going to cover all the technical details here, but the undocumented API works as RPC client, and ngc import symmetric pop key can talk to lsas.exe, and then lsas.exe works as RPC server and import the encrypted session key into TPM and decrypt it by the registered transport key in TPM. And ngc sign with symmetric pop key can use the session key decrypted in TPM and sign the signing input and get the signature of session key from the signing input. So by analyzing the undocumented APIs, I figured out that we can use them to import and decrypt the session key in TPM. Then we can use the session key for signing. So with this approach, we can finally sign the PLT with the decrypted session key, and we can also create our own PLT cookie. So I implemented this into my POC, and I confirmed that we can create our own PLT cookie, as you can see here. Now we can create arbitrary user's PLT cookie with a credential, so we can gain browser single sign access to resources as any user if you have the credential. So let me summarize what we have seen so far and how we can abuse them. First, we need to infect some corporate machine that is registered to Entra ID, And then from the machine, we can sign any user's login request stored in device, signed by the device key. And then you can send the signed login request with the signature of device key, and you can get the user's PLT, and also you can get the encrypted session key. And after that, you can import the session key to TPM and decrypt it by the transport key stored in TPM, thanks to the undocumented APIs. Then you can sign the PLT with it, and you can create PLT cookie. And if attackers get the generated PLT cookie with this approach, attackers can pivot to the cloud as a user of the PLT cookie and bypassing the device-based conditional access. So with this approach, now we can gain the browser-based single sign access. But what if I want to have API access to Entra ID? So there is another authentication flow that can give us app tokens for API access. So by sending the PLT signed by session key, we can also acquire app tokens for API access. However, these app tokens in the response are encrypted, and they cannot be used as they are for API. But actually, you can decrypt the encrypted app tokens by the session key. And I found that there is another undocumented API used for us, which is the NGC decrypt with symmetric pop key. So by analyzing the usage of the undocumented API, I confirmed that we can decrypt the encrypted app tokens with the session key decrypted and stored in TPM, and we can acquire access token and also refresh token for API access to the cloud as well. So by abusing the TPM stored keys through the undocumented APIs and also the internal function of Azure AD plugin loaded in LSAS, we can create our own PLT cookie, or also we can acquire app tokens with any user's credential. And this attack approach does not require administrator privilege in the compromised device. And using this approach, we can finally bypass the device-based conditional access policy. So now the initial goal is achieved, but let's explore more to find another ways of abusing the TPM stored keys. So another abuse of the TPM stored keys is passwordless authentication. So I found that the other imported APIs allow us to interact with the Windows Hello for Business keys stored also in TPM. First, let's look at the Windows Hello for Business implementation to find out what these undocumented API can do for us. So as you might know, Windows Hello for Business is used for passwordless authentication. And when you want to use it, Windows Hello for Business keys called user key are generated and registered to Entra ID. And after that, this can be used to authenticate to Entra ID without password. And when authenticating with Windows Hello for Business, first we need to send device key signed JWT that contains the user key signed data. I know this is kind of complicated. Then Entra ID can return the PLT and also the session key. With this, we can create the PLT cookie as we have seen before. So let's look at the complicated signed data. So this is the request to Entra ID during the authentication. And it has the device key signed JWT in the request. And if you look at it, the JWT's payload contains data with the signature of Windows Hello for Business keys. And Entra ID received this request, and with this request, Entra ID can perform its authentication by validating the key usage of the device key and also the Windows Hello for Business keys. So by analyzing the undocumented APIs and by interacting with all the secret keys stored in TPM, I confirmed that we can authenticate to Entra ID with Windows Hello for Business keys without password, and we can create PLT cookie. And also, in addition to the PLT cookie, you can also receive access token with the Windows Hello for Business keys. And if you look at the access token here, actually acquired by this approach, this access token has MFA claims in its payload. So this means that with this authentication approach, multi-factor authentication is already completed. And also, you can see there is a device ID here in the claim, in the payload, which means that device identification is also completed with this authentication approach. So to summarize, now we can create PLT cookie, or also we can acquire the app tokens through Windows Hello for Business keys without password. And this approach allows us to bypass the device-based conditional access policy, and also attackers can bypass the MFA enforcement policy in the conditional access of the Entra ID. However, there is one bad side for the attackers. If you want to log in as other user, if you want to switch accounts, then you need to compromise other device with Windows Hello for Business keys stored. So the Windows Hello for Business keys are bounded to a specific user and stored in other device. So if you want to move laterally between accounts in the cloud, then we have to compromise other device with other users' Windows Hello for Business keys stored. So let me show you a demo. So I implemented all the techniques into PowerShell, script called bad token broker, and let me show you what it's like. Okay, so right now you are looking at the Windows 11 box, and this is registered to Entra ID, so you can access to Microsoft. And now there you can see attacker's machine. And for the demo, first I will try to log into the Entra ID and pivot to the cloud with the stolen credential in the introduction. However, from the attacker's machine, the access is blocked by the conditional access. And it looks like it requires the corporate device, like the Entra joined and on-premise AD joined device. So let's imagine that we compromise the Windows 11 box, and we can open the PowerShell session, and we can import the bad token broker script like this. And we can execute the create PLT cookie command by specifying the username and the password. Once you execute it, you can get the PLT cookie like this. And then once you get the PLT cookie with this approach, you can go back to the attacker's machine, and you can configure the PLT cookie in the browser cookie store like this. And then once you configure the cookie, you can access Microsoft again. And now you can bypass the device-based conditional access policy. So this is all for the demo. Okay. So I implemented all the techniques into the bad token broker. Now it's public, so you can access to the URL specified here. So this is all for the demo. And finally, let me give you some tips for mitigation against this attack. So this attack is implemented based on how Windows OS internally handles the secret keys stored in TPM. So it's kind of like by design. And Microsoft has responded to this attack as an expected behavior. So there is no fix so far. However, for the mitigation, I recommend you should review and harden your conditional access policies for example, requiring MFA, not only just requiring corporate device. And this helps to make it harder for attackers to pivot to the cloud and move laterally between accounts in cloud. So during our team engagement, we have seen a lot of companies require just only corporate device to access the cloud, not require MFA. But if MFA is also required, then attackers have to do something like compromising other device with the Windows Hello for Business keys configured for switching accounts for their post-exploitation activity. So I recommend you should require MFA and harden your conditional access policies so that attackers will be hard to pivot to the cloud. And to detect the attacks by the bad token broker, you should monitor suspicious RPC activity by using the internal function of Azure AD plugin, and also you should monitor the cryptanalysis and documented API calls. Also, if your corporate device is compromised, then it is a good idea to check if the device is used by attackers to bypass the device-based conditional access policy and move laterally between accounts. You can look at the multiple account sign-in logs from your device. Please refer to the KQL query listed here. So let me summarize today's session. So we have seen how attackers can interact with the secret keys, even stored in TPM, thanks to the RPC calls and also the undocumented API. And once your corporate device is compromised, then attackers can easily abuse them for bypassing the conditional access policies, as we have seen before. And for making it harder for attackers, I strongly recommend review and harden your conditional access policies more and detect the suspicious activities in your endpoint. So this is all for my presentation. And if you have any questions, I'll be around here, so you can walk to me and ask any questions after the session, or you can send some DM to Twitter or LinkedIn, whatever, anytime. So this is all for my presentation, and thank you very much for listening.